Taiwan and is a specialist in ocean optics and remote sensing. So please, Doctor, start your presentation.
Thank you, Chairman, and good afternoon, ladies and gentlemen. I think we have a long coffee break. It's all right. Let me start by introducing myself. I'm Cheng-Chien Liu from National Cheng-Kung University. I'm with the GEODAC, Global Earth Observation Data Analysis Center. I'm from Taiwan. I would like to express my gratitude to the organizing committee for inviting me to come here and share the topic, multi-platforms of remote sensing for sustainable coastal development. This topic is very important in Taiwan. Why is that? Well, as you probably don't know, because of frequent earthquakes and typhoons, as well as steep mountains, make Taiwan the highest erosion rate in the world. This animation shows here, it's satellite images that showing a lot of tremendous amounts of landslides triggered by one single typhoon. All these materials will be delivered by rivers and eventually dumped into the coastal region. So this photos is actually was taken in the Gaoping River mouth, which shows a very high sediment loading. In some cases, this will cause the problem of abrupt deterioration of water quality and will stop the domestic water supply, which is a very serious problem for any country in the world. Not to mention that we have the problem of eutrophication, coral reef bleaching, oil spill, and sewage pollution. So we have a lot of problems for coastal regions. And we really need to have systematic and regular measurements. So that's the reason we go for this approach, multi-platforms of remote sensing. This is not just a concept of we would like to see things both in details and the whole pictures. This is also a practical approach. We are trying to integrate various data, all available data from all kinds of platforms using various algorithms or softwares and try to provide a service. And these are exactly what I've been doing for the past 10 years. And the main intention of this talk is try to share some experience we have and hopefully initiate some collaborations in the future. So I'm summarize these works and I'm going to give this talk following this outline. First, let's start from the remote sensing of ocean color, because this is the first satellite mission dedicated for oceanography, and it has the name Coastal Zone Color Scanner. The colorful animation you see here is widely used to illustrate life on the Earth, both for land and the ocean. But to be precisely, these are just the spectral signals detected by satellites, and we call this apparent optical properties like remote sensing fluctuance, water-leaving radiance. And what we really concern is the constituents of water, like chlorophyll A, total suspended matter, and so on. And to link these two AOPs and the constituents is the inherent optical properties. Based on the radiative transfer model, by solving the classic radiative transfer equation, we will be able to convert from IOP to AOPs, and the bio-optical models can describe the relationship between IOPs and the constituents. So depending on what given conditions you have or what unknowns you are going to pursue, we can categorize this problem into the forward problem and the inverse problem. For the case, if you have some output from like a biogeochemical model, you have this chlorophyll concentration, then we can use the numerical approach, like a Monte Carlo approach, to simulate a beam of light as large numbers of photons. Then we can follow each photons and use a series of physical process to simulate, to predict what the satellite will see. So we can estimate the spectral signal, and that will be the satellite signals we detect from, we derive from ocean color images. And for the case of Lee Stocking Islands in Bahama, and this kind of sand wave features revealed by airborne images actually can be simulated by the three-dimensional backward ray tracing Monte Carlo model. And we will be able to investigate what kind of factors can generate this kind of features. Okay? So this is the three-dimensional version of the Monte Carlo backward ray tracing. Comparing to the real satellite observation, in this case, you can see it's quite spicy. And we can summarize the satellite observation and quantitatively compare to the model simulation. In that case, we can provide a quantitative assessment of this model performance. In this case, the spring bloom is a little bit late, and the scale is too high, and duration is too short, and so on. Well, when it comes to the inverse problem, and we need to use the satellite observation to derive the constituents, and we can apply different approaches of optimization, like genetic algorithm or the spectral matching approach. That will give us more than chlorophyll A. It will give us like the concentration of total suspended matter, CDOM, and inherent optical properties. And together with the underwater light field, underwater light model, we will be able to retrieve the underwater light field from sea waves observation. In this case, this is our West Florida shelf. We can map the compensation depth, which is very important for in terms of biology. We can simulate, we can map the depth from remote sensing. And because nowadays there's a lot of ocean color data available, and we can compile a lot of MODIS data in Taiwan, so we will be able to categorize the dispersal patterns of river plume in Gulping River. And in this case, we can simulate not just chlorophyll A, but also CDOM and non-algae particles. And this is a frontal pattern happening in the winter time when the branch of Kuroshio intrude to Taiwan Strait, and there will be a strong current, coastal currents. So you will see this kind of frontal patterns. And in some cases, for example, extreme weather event like a Category 5 typhoon overpass, it will act like a pump and suck a lot of nutrient waters, cold water from the bottom, and create this kind of short-term but large-scale spring bloom. And if you are lucky enough, you have a very short period of time with satellite observation, and we can detect this kind of short-term but regional large-scale phytoplankton bloom. So this work indicates that the general ocean color data, spatial and temporal resolution might not be enough to resolve the dynamic change in coastal region. So we have to seek for the other source of data. And nowadays, there's a lot of land-based data available. For example, USGS has a long history of Landsat observation, and in Taiwan, we have our own satellite, Formosat 2, which has 2 meters resolution. But the challenge is there's no rigorous atmospheric correction for that kind of land-based satellite. So in this work, we propose an approach and make assumption, because all these satellites are operated in the sun-synchronous orbit. So we can assume during that short period of time, the atmosphere does not change a lot. So we can use the parameters derived from MODIS and apply that parameters to correct the land-based satellite like Landsat and the Formosat 2. So with this approach, we will be able to derive this kind of product, which has 2 meters resolution, total suspended matter concentration. So we can see a lot of details. Another way to circumvent the problem of atmospheric correction is to make a lot of field survey to measure the reflectance from the ground. And in this case, this is the largest reservoir in Taiwan. We call it Cheng-Kung Reservoir. And we have a series of satellite images taken by Formosat 2, it's 2 meters resolution, and we apply some kind of radiance normalization, and we will be able to get this time series observation. Then we went to the reservoir once per month, and we do this measurement, and we took the samples, analyzed in the lab. We will be able to derive an empirical algorithm dedicated to that region and for Formosat 2. So we will be able to map these water qualities using Formosat 2 land-based satellite. And although this is the largest reservoir in Taiwan, but if you use like a MODIS, it will be only just a few pixels. We won't be able to do this kind of detailed mapping. So it turns out that land-based satellite is really useful for coastal region, and because this is our own satellite, so I can compile a lot of images from year 2004 to year 2009, all available Formosat 2 images, and do the analysis, processing, and we will be able to clarify the relationship between the plume cone size and precipitation, and we can understand the mechanism behind the frontal pattern and study some influence of typhoon events and show the case of special case flushed by 2 rivers. Well, anyway, this work demonstrates that we really need a stable, continuous observation from the sky. They will be very useful for coastal study. Unfortunately, our satellite Formosat 2 ceased to work in late June this year, well, after 12 years of operation. And actually, 2 years ago, we've been considering this kind of situation, so we start to expand our capacity of image processing to process the Landsat 8 images. And what kind of images we will have, and this is an example. Now we have an image processing system which allows us to process the raw data from Landsat 8 and all the way to the final product and publish on the website, allow the user to access. And I checked, this is the map of existing Landsat 8 ground station and its coverage. To my surprise, Dubai is not covered by any ground station. And it's okay, you don't need to spend money to buy an antenna license. Everything can be downloaded from the USGS, but you really need to have a system which can help you to convert from the raw data to the useful product. And this system can it takes only about 10 minutes to process one thing, including publish on the web. And I've already done this for Taiwan, and we have a service, we call this very easy to memorize, OASIS, Open Access Satellite Image Service. If you go to this site and you will have this interface, which allows you to select any day you want, and it will show the images. And if you click on this button, then it will download the images. It's a JPEG images, compressed file, but it's full resolution. Then you can actually view the image and zoom in to the details. So you can see with 15 meters resolution, it reveals a lot of details in the coastal region. Okay, so I've already done the whole thing for Taiwan. It's operational. And to express my gratitude for inviting me here, I asked my colleagues to do a quick version for Dubai as well. So the name is a little bit lengthy. You have to go to this OAGIS. It's a Geospatial Information System. And GEODAC, that's the name of my center. And you have to put this Dubai. Okay, then in this system, you can download actually. That's the system. You can download all the lens set. I shouldn't say all. I only select a few of them, so you can see. But you can download each image. You can turn each image on and off, and just use it as a Google map. You can zoom in to the highest resolution. For example, before I came here, this is my first time here. I'm curious. So I can check, well, this will be my hotel. And I double check with my window, yes. And of course, 15 meters resolution might not that clear. But you know, nowadays there's a lot of open data available. European Union, they have launched a series of satellites, Sentinel series. And the Sentinel-2 is now officially operational, and it provides 10 meters resolution. So I also download one Sentinel-2 scene and process and publish on the system. You can see the resolution is much higher. So in other words, nowadays you don't need to have your own satellites. That costs a lot. But you should make the best use of all available data. And not just get the data and lock it in your desk. You should process the data and publish on the web and let everybody to use it. I think that's the essence of having the data. We've heard that today, right? Okay, that's the part of land-based satellite. And how about general ocean color satellite? Actually, there's a trend. They've already lifted up the orbit from the sun-synchronous orbit to the geostationary orbit. That's the case of Korea's satellite called GOSI. It was launched in 2010. It's amazing because it's very far from the Earth, but it can give you 500 meters resolution 8 times per day. Well, you might ask, why go to geostationary and this coverage doesn't cover Dubai? Why bother to study that? But if you check the future, the schedules, there are at least 3 geostationary missions are scheduled, including NASA's GEOCAP and the Indian's mission. The most important is GOSI-2 will be launched in year 2019, and that mission will be global coverage. So all the efforts we make now should be paid back in the future. Okay? So with this kind of geostationary observation, what information can we have? Let me use this as an example. This clip, this video, this small movie is made from 2 days observation, totally 16 images. 500 meters, 1 hour temporal resolution. So you might have the same question as I have. What kind of dynamic information would be useful to derive from this kind of observation? And it turns out to be the surface currents, because this kind of spatial and temporal resolution would be ideal to study the mesoscale currents or eddies. So we've been doing that, and this is an example. If you have 2 images taken just within 1 hour, then you can apply, this is nothing new, a lot of works. You can apply this kind of image matching and find out where matches the best. Then you can derive some kind of track. And this is an example. It's in the west northern Taiwan. And we can have this kind of product. Each color means each different time interval. And this clearly shows the tidal current, reverse flow. Okay? And this is another example. In the West Pacific, different country, different region, you will have very different type of current. Okay? And every time when I show this to physical oceanographer, they will be very interested because this will be the perfect data set to validate their model or even to serve as a boundary condition to drive their model. Okay? Of course, we won't have this kind of product every day because if you have cloud cover, then nothing can see through. But as long as there's a clear sky, we will have a lot of, we call this nature treasure in the coastal region, and you can use that to derive the time-derived product. And I have already processed all GOSI data. It's a collaboration with Korea. They provide me all the raw data, and we process, and we publish on the website. So if you go to, again, the old Oasis website, and you can select the image you want to see. And first, you switch to the center of GOSI images and select the day and the time, and you can see that's the image. And the beauty of GOSI data is the temporal resolution. So in this system, you can actually select the start time and the end time and do the animation here on the web. But it depends on your internet speed because there's a lot of images. But because we have already do the image type processing, so it should be fine. And you can zoom in to the region you are interested in. In this case, we can zoom into mainland China, the coastal region. There's a lot of sediment. And you can do this animation again here, so you can see in more details. Okay, that's GOSI data. Now, let's come to another subject. In some cases, you really need a high-resolution imagery. Then we try to use this kind of unmanned aerial vehicle. This morning, I went to the exhibition hall. There's a lot of fancy, advanced vehicle around. Yes, it's getting more cheaper and more powerful. But what kind of vehicle should we choose? In this case, fixed wing give you a better wind resistance, is faster and long duration, is ideal for mapping. And that's the case we have. I only can afford that. Now I should say, this is easier, more flexible. You can launch the vehicle by your hands. And the key thing is you need to have a good mission planning. We deploy this in a coastal region just before a typhoon is coming, so the wind is very strong. And this kind of fixed wing UAV can resist the wind and give you a very good map. Of course, there's another type of UAV, multi-axis drone, and it's getting cheaper. And this one will give you a larger payload. You can put a better camera, and you can fly it low and make a lot of pictures. So it turns out to be ideal for digital surface model to derive this digital surface model. In this case, we try to count the number of special bird. This bird called the black-faced spearboom bird. There are only 2,000, something like that in the world. It's an endangered species. And it's very important to count the number every year. But usually they just sitting on the ground and use their naked eyes try to count. And we use this kind of techniques can give you a more accurate numbers. And we also did some works for digital surface model. And let me show you this small movie. This small island is also part of Taiwan, even though it's in just besides mainland China. And there are some engineering works. They try to build a big pipeline, but you have to remove these trees. But some of the trees are very precious one. So they have to tell which trees is which. And we can use this. You see the height of the tree and the colors, the texture, everything can be revealed by this high resolution UAV images. As long as you can process the image to generate this kind of digital surface model, it will be very useful. Okay? And in some cases, you cannot see just from the sky. You need to actually touch the water, make measurements in the water. So it turns out to be another vehicle we should consider. It's an alternative to satellite and research cruises. If you want to do this more regular and more systematic. Now we have this kind of, you can call it glider or autonomous underwater vehicle. And it's a very expensive one. I cannot afford to lose it. So in this ongoing project, we are trying to establish some kind of standard operational procedure in a large lagoon. And it turns out to be very useful. That's the temperature measured by this AUV in the low tide and high tide. And if you overlap with the sewage system, then you realize this lagoon actually is very close to the factory house. So a lot of water, wastewater, sewage water will be dumped into this lagoon. So different time, during the low tide and the high tide, you will have very different story. And you can check the salinity, and you will realize there are some wastewaters for fish farm, and it brings a lot of nutrients. Okay. Everything you collect, spend a lot of time, efforts, money. If you don't integrate them, if you don't share them, then those are just the digital garbage. So for geospatial information, I think the most important thing is you need to have a good method to share, to integrate, to display them. And now everybody would like to use the web-based platform because you don't need to buy an expensive software. And that's the reason why Google is so successful. But there are some problems with Google you probably don't know. For example, in Taiwan, in the beginning it's free, but later they introduced some kind of enterprise version, Google Earth Enterprise. It costs a lot. I think $200,000 US for one globe. And Taiwan purchased 48 globes. Everybody got their own Google Earth Enterprise. But just in the end of last year, they stopped the service. Well, they have some kind of security or internet or whatever. And all the service stopped. So it caused a lot of problem for governments because they relied on Google Earth too much. So and another problem is we really need a true mobile solution. If you use Google, every time you stop the system, it has to go to check the web key from the internet. So that means you cannot bring this system to the mountain area without internet service. So considering that, now they have an open source called Open Layers. So we build everything on Open Layers, but we still have to use Google Earth resource, like their panoramic images. So the strategy is we follow the KML standard and we process our image that can be displayed on both Google Earth, Google Map, and the Open Layer system. So that's the system I've just showed you now we've done everything on the system. So that's the device version. I'm sharing this with you. You can also publish your UAV images. For example, this is in Taiwan, and from this system you can view the images easily at the highest resolution. Okay, so no matter what kind of images you have, you can always use this method to share with your colleagues or even the general publics. And not just the UAV images, but also the data you collect from autonomous underwater vehicle. You can do the same thing. Okay. Let me quickly make a conclusion. As I explained, this kind of multi-platforms of remote sensing is very useful, very important for coastal zone studies. And we've been endeavoring to employ this concept, this approach to study the coastal region. And we have already integrated all this data from different platforms. And we will also try to establish our own platform or our own algorithm. But the most important thing is to put everything into a shared, web-based system to share with colleagues, to share with general publics. And this I put in red color is something I think is mature. We can quickly to share with you. So now I have several projects continuously supported by Taiwan government. So we will do our best to improve the platform and image processing. And we welcome any type of collaboration. Okay, that ends my talk. Thank you very much.
Thank you, Dr. Liu. It was very, very interesting talk. I'm sure the end will be very interesting too. And it's a keynote speaker, so we don't have questions. But of course, Dr. will be around.
Yeah.
And will be more than available. So thank you very much.
Thank you.
Our next speaker is Dr. Paul.
Excellent.
Flicker.